In this video, we will discuss the only advanced method of integration we encounter in Calculus 1. Though certainly later on in this semester you will encounter many more advanced methods of integration. But for now, as I've mentioned in a previous video, we are in a great position to integrate. Either you can get to one of your common formulas through algebraic simplification, or if not, your only other approach is really to use what we're going to call a substitution. Now, substitution is a method of integration that undoes the chain rule. So we use it to differentiate functions that have this form to it. And what I look for is kind of this function derivative pair. You want to find a function that appears inside and its derivative appears outside. When we do so, what we will do is we'll call that inside function u. So the substitution that we make is we say u is equal to g of x, and then from a differential perspective, something else discussed in Calculus 1, du would be the derivative dx. So looking over here, we see the g prime dx is our du. And what a substitution does for us is it doesn't technically solve the integral. What it does is it takes this maybe difficult looking integral solely in terms of x, and it rewrites it in terms of this simpler, easier to evaluate integral. You evaluate that integral, and then you resubstitute to get it back in terms of x. So let's see this in action. We will now use a substitution to evaluate the given integral. And let me just note that if the question had been phrased differently, just evaluate, what is our thought process? Well, we think, can I somehow algebraically break this up so I can use my common formulas? And no, a square root never breaks up over addition, so the only real choice here is a substitution. We want to pick u to be an inside function, and we want to pick it to be the largest possible inside function. So in this case, we'll let u equal x plus 1. And note, if you let u equal to x, that would give you back the exact same integral, so we need more than that. So u equals x plus 1. So du is the derivative of x plus 1, 1, times dx. So the dx simply becomes the du. And remember what our goal is. We want to go from this beginning integral, which is tough to evaluate. It's solely in terms of x's. We need to write it solely in terms of u's. And there's no middle ground, all x to all u. So this becomes this integral of square root u du. And the idea is that this resulting integral is going to be easier to evaluate. So let's do it. So square root u is u to the 1/2. 1/2 plus 1 is 3/2. So we have 1 over 3/2 u to the 3/2 plus c. And as the last step, remember we need to get it back in terms of that original variable. So we take whatever our substitution is, and we call this resubstituting. So we take this u equals x plus 1, and we plug it back in for u. So this is 2/3 x plus 1 to the 3/2 plus c. So one more example of an indefinite integral with the substitution property. Now our thought process is exactly the same. Looking at the integrand, I have no algebraic techniques to simplify this and get it down in terms of powers of x. So my only choice is a substitution. And for a substitution, what I need to do is pick u to be an inside function. And the only inside function I see here would really be this x plus 1. So just like the previous example, we're going to go ahead and let u be equal to x plus 1 so that du is still dx. So the dx can become du, and what we need to do is go from all x to all u. But we have this pesky leftover x. And whenever that happens, when you have an additional x, we need to write it in terms of u's. And the substitution itself is the relationship we have between x's and u's. So x is equal to u minus 1. So looking at that substitution, that allows us to rewrite this x as u minus 1. So we now have the indefinite integral of u minus 1 square root u du. So we go from all x to all u. So that substitution does not solve the integral, but what it does is gives us an easier to evaluate integral. So let's evaluate. So remember, square root u is u to the 1/2, and we can distribute that through. So this will be the indefinite integral of u to the 3/2 minus u to the 1/2. And then anti-differentiating term by term, 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. And you want these more familiar antiderivatives just to become almost second nature to us. And now we resubstitute. We need to take every u that we see and replace it with an x plus 1. So this becomes 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. And as a reminder, every indefinite integral needs to have the plus c, and whatever the original variable of integration is, that is what your answer should be in terms of as well. Also throughout, we should be using good notation. Equal signs at each step, du's, dx's until we have evaluated.